Hi everyone, welcome to Optimization Methods. Today we will introduce the second part of Chapter 9, the exact penalty method. So recall that in this chapter we are trying to solve the constraint problem with equality constraints and inequality constraints. So we try to use the way that we transfer the constraint into the unconstrained problem. Okay, so in the previous part, we introduced that we transfer the constraints in terms of quadratic penalty method, and we solve the resulting unconstrained problem. So there is another way that we transfer the constraint in terms of penalty function by absolute values. Okay, so let's take a look at the non-smooth penalty method, which is also referred to as L1 penalty method. In L1 penalty method, we just penalize the constraints in the absolute value here, okay? So for equality constraints, we just put the absolute value here and do the summation. For inequality constraints, we take the maximize of 0 and the non-negative part of equality constraints, then we put them directly into the objective function. This will become the L1 penalty function here. Okay, so in other words, we replace the L2 penalty function into L1 penalty function, and then we get the L1 penalized problem. So we have some remarks about the exact penalty method. Actually, for exact penalty method, why we call it exact? Because it has a nice property, meaning the exact recovery property. That is, by choosing a proper penalty parameter mu, the resulting penalty method have the same solution as the original problem. Okay, so recall that in quadratic penalty method, we have to drive the parameter sigma to be infinity in order to get the original solution for the problem. And now here that we have no need to drive this penalty parameter mu to infinity. Okay, so we just choose a proper one, then we can get the exact solution of the original problem. Now, let's take a look at the example here. We get a very simple example in one-dimensional space where we try to minimize x, and we have a non-negative constraint that x must be greater than or equal to 1. So to see the constraint and the objective, we can easily find that the optimal solution is achieved at x star equals 1. And if we take further look at the L1 penalty function, it actually takes the following form, that we multiplied the violation of the inequalities by a penalty parameter mu, and since this is an absolute value of max, then we, according to different cases, we can write the L1 penalty function into two parts. Okay, if x is smaller than or equal to 1, then this will be a violation, and we add the penalty term here. So the objective becomes the term like this. And if x satisfies the condition, meaning that at x is greater than or equal to 1, then the function value takes the original one, which is x. So in other words, for the one-dimensional example here, we can actually plot the figure of this L1 penalty function, and by taking the minimization of the L1 penalty function, we can find the minimizer. Okay, so below we demonstrate the figure of the penalty function. As we can see that this is a kind of penalty function. So the left-hand side is just a penalty one because in this case, x violates the constraints, okay? And when x is greater than 1, then this is the original function, okay? And for this case, you can see that if mu is greater than 1, then we have the figure like this, okay? Where the optimal solution is achieved exactly at 1. However, if we choose penalty parameter mu strictly smaller than 1, then the penalty function takes the shape like this, where x equals 1 is not the minimizer of the problem, okay? Because for the part here, we can actually see that this problem is unbounded, okay? Therefore, for L1 penalty function, the parameter mu have to be chosen carefully, and it has no need to tend to infinity, okay? Now, let's take a look at how we do the exact penalty method. So, the framework of the algorithm is demonstrated here, where it is very similar to the quadratic penalty method, actually. So, in the initial point or the starting point, we still choose a penalty parameter mu0 and tolerance tau, as well as a starting point x as 0. Then we start the loop in the following way. So in each iteration, we find an approximate minimizer about this L1 penalty function with the starting point at x as k. And if the measurement of violation is smaller than or equal to tau, then we will stop the inner solution and then we return the current iteration xk. Alright, now we check whether we need to stop the outer loop. If the stopping criterion is satisfied, then we stopped with the outer loop. Otherwise, we need to choose the next new penalty parameter to be greater than the current one, and then we choose a new starting point for the next loop. And the iteration goes on until the final stopping criterion is satisfied. Now, let's make a brief summary about the exact penalty method. The exact penalty method basically means that we take the penalty function as the L1 penalty function to do the optimization process. Okay? There is a good property about the exact penalty function. However, when we try to solve the inner problem, we actually may get some difficulty because the objective function is non-smooth. Anyway, we will leave this problem to the future, which we will discuss how we solve non-smooth problem. Okay, we stop this part here and see you next time.